Hello, in this video, we are going to look at some buffer systems, how to calculate the pH of a buffer, and then when we add an acid or when we add a base to a buffer, how do we do those? So bear with me through the whole thing because this will be great for especially exam type questions that at least I like to put on exams. So the first one here is just the pH of a buffer. And when you're dealing with a buffer, the nice thing about that is there's an equation that you can use to find the pH. It's called the Henderson-Hasselbalch equation. It is the pH is equal to pKa plus the log of the ratio of the conjugate base substance divided by the weak acid substance. All right. Now there's a pOH version of this same equation that you can use for weak base systems. How I make my decision which one I'm going to use depends on if I've got a Ka value, I'm going to use this version. If I have a Kb, then I use the other version of that. So it doesn't really matter though. They work the same way. In theory, there's a way to even use either one of them for your problem. So that's the Henderson-Hasselbalch equation. So really just two things are needed to find the pH. Well, three, I guess, if you look at it this way. But the two things, that how I'm thinking of it is you need the pKa value, and then you need the ratio of the conjugate base over weak acid. You can use mole amounts there. Notice I didn't put them in as a concentration. They can be mole amounts, they can be millimole amounts, or they can be concentrations. The thing you got to remember with concentrations is it's got to be the concentrations after mixing everything. All right. So it's really easy on this first one to find the pH of this particular one. So first thing we need is the pKa value. How you find the pKa, let's go ahead and do that over here. pKa is just the negative log of the Ka value, which in this case they gave it to us is 2.4 times 10 to the minus 6. And so when I plug that into my calculator, that is 5.62. All right, that's the pKa. Here's the nice thing. As long as you're using this particular acid and its conjugate base, that's going to be your pKa value. All right, you can use that over and over. As long as you have a buffer solution and you need the pKa value, it's always going to be that 5.62 value for this particular acid. I just made a generic weak acid, HA, and then this sodium salt contains its conjugate base, A-. All right, now for this particular problem, the concentration amounts they've given to us are for this 125 milliliters of buffer. So those are the after mixing amounts in this case. So we can use those directly. So we're ready to use that Henderson-Hasselbalch equation, pH equals pKa. I shouldn't write it in there. I can just write the number, 5.62 plus the log of the A- goes in the numerator. The conjugate substance always goes in the numerator. That's going to be the sodium salt concentration. The sodium's just a spectator here, but that A- ion does affect that. So I'll put 0.18 moles per liter. That is the concentration of this 125 milliliters of solution, again, of A-. And then the denominator is the 0.35 moles per liter of the HA, the weak acid that goes in there. All right, so depending on your calculator, you may need to stick some parentheses around that so it gets that ratio. The way I work this on my calculator, I have an older calculator. I take the 0.18 divided by 0.35 first. I hit equals, then I take the log of that. Make sure you don't change the sign on that. In this particular case, so we've still got the 5.62 plus the log of our ratio here is a negative 0.29, negative 0.29. So I'm going to add a negative 0.29 to this, and that gives me my pH of 5.33. And there's my answer. All right, to get the pH. It's super easy. If it's just a buffer by itself, then you just need those three things. You need the pKa, your amount of acid, and the amount of conjugate base. What makes it a buffer? It's got to be a weak acid and its conjugate base, or it could be a weak base and its conjugate acid as well, right? Both of those will make buffers. Now, there is another way I'll show you real quickly how you could find this. Like I said, you can leave those as concentrations if they're after mixing concentrations. If you have a problem that says this weak acid was mixed with this sodium salt that contains the conjugate base, then what you do is just a volume times concentration. Now, in this particular case, you're going to get the exact same answer. But let me show you how you would do that. Same pKa, you find it the same way we did before, negative log of that Ka value. plus the log of. So instead of just the concentration, I would take the volume times the concentration, especially if I was mixing two different solutions. So I would take the volume of the acid times the concentration of the acid, and the volume of the conjugate base times the concentration of the conjugate base. In this case, they both happen to be in 125 milliliters of solution. So to find my moles, or in this case, it would actually be millimoles of the sodium A- salt, I take the 125 milliliters times 0.18. Divide that by, for the acid, now again, in this case, it's in the same 125 milliliters of solution, times its concentration of 0.35 moles per liter. But if you had different sources of the weak acid and its conjugate base, then you would just plug in whatever their volumes were in here instead of the 125. If you had, say, 50 milliliters of the acid solution and 25 milliliters of the base solution, you could just plug those numbers in directly. Obviously here, the 125 just cancels out, and we're right back to the 0.18 over 0.35, which is what we had in the first place. So you won't always need to do that. But like I said, a lot of times what I teach my students is to have them do that volume times concentration. That gets them the amounts that they need there. All right, so that's the pH of the buffer by itself. All right, and so let me go on to the next slide here, make sure it changed over. So again, the pH of the buffer by itself, we said was 5.33. I'm just going to write that up there just so we've got it, and we can kind of compare for this next problem. So the next thing we're going to look at is now what happens to that buffer when we add another substance to it that could react with one or the other of the components. What makes a buffer special is it's got an acid component and it's got a base component. So when you add in some other acid, like we're going to do in this problem, there's a base component that's going to react with this. And so if you've watched some of my other videos, you may have seen my 6-step sequence that I use to figure out the pH of a solution. And so that's exactly what we're going to follow here. Step number 1 is to write out the reaction. So let me do that over here. Make sure this will show up all right. All right, so there's the HCl. Always start with the substance you're adding into the buffer. That's going to govern what part of the buffer you're going to react it with. So in this case, we've added HCl. Again, don't start with your buffer components because you're going to get confused. Start with the substance you're adding into the buffer. So in this case, HCl, what kind of compound is that? Do you know? You got to know this stuff, right? HCl is a strong acid. All right. Right now, it doesn't matter that it's strong. What matters is it's an acid. You got to be able to recognize it as an acid. And so that's going to tell us then what part of the buffer that strong acid's going to react with. I've got two parts to this buffer. I have an acid component, HA, and then over here, I've got the conjugate base component, the A- that comes from that sodium salt. I don't care about the sodium. The sodium here is just a spectator. It's that A- ion that's part of this buffer system. So the acid that we're adding, the HCl acid, that's going to react with the base part of the buffer, the A- ion. You could write it as sodium A if you wanted to, but the sodium's just a spectator, so I like to leave that out. All right, so those are your reactants. That right there, that's the hardest part for a lot of students, is just figuring out that particular part of this reaction. All right, so now we can write out what our products are. We're going to transfer a hydrogen over from the HCl to that A-. That's going to make HA, this weak acid. Now, our solution's already got some HA in there. We're going to make some more. What else do we get? When the hydrogen leaves the chloride ion, that leaves us with just some chloride ion in there. So there's your reaction. All right. For a lot of students, that's where they get hung up. The rest of, they know how to do ice calculations, but if you don't have the right reaction, that makes it really difficult. Next step, what are your pH players? Go substance by substance and ask yourself, if that was the only thing in solution, would that affect the pH? And HCl definitely affects the pH. It's a strong acid. How about A-? Well, A-, it's a part of this buffer, and it is the conjugate base of a weak acid. The conjugate base of a weak acid will affect the pH. All right, the weaker the acid, the stronger its conjugate base will be. It's going to affect that pH. So A- does affect the pH. And finally, HA over here, it's a weak acid. That's going to affect the pH as well. So this is a case, unlike our strong acid, strong base example that I did a few minutes ago, or in another video, none of the products there affected the pH. Here, one of the products affects the pH, that HA. The chloride ion, on the other hand, let's finish it out, that does not. Why not? That's the conjugate of a strong acid. Remember, the stronger the acid, the weaker the conjugate base. Since HCl is one of the strongest acids, chloride ion is one of the weakest bases. It's so weak, water is a stronger base than chloride ion. We get more hydroxide from water than we would from chloride ion, is the way I like to think of it. All right, so there's our pH players. Next step, now let's figure out the mole or millimole amounts of those. Then we're going to be ready to do our ice calculation. So for HCl, let's go substance by substance here. HCl, we're going to take the volume times concentration. It's 15 milliliters, and we're going to multiply that by its concentration, 0.25 moles per liter. That gives me 3.75. And again, this is going to be millimoles here. All right, if you want moles, divide by 1,000. You divide the 15 by 1,000 to make it liters, so you divide this by 1,000 to be 0.00375. I like millimoles. I don't like getting hung up on it. It always has to be moles. Some books, everything's moles, and they never even mention millimole amounts. It's just they're cute little moles. They're tiny, 1,000th of a mole. Anyway, next is the A- ion. And so volume times concentration there. The A- is coming from that buffer solution. We've got 125 milliliters of the buffer solution. And the concentration of the A- component is 0.18 moles per liter. And so volume times concentration there. I try to use just, some weird numbers here because you don't always get regular numbers when you're doing, I put 3 M's in there, when you're doing a calculation. All right, so I try to use some more strange numbers for that. And then finally, we also need the HA. A lot of students just leave that out. Don't leave it out because it's there at the beginning of this reaction. It affects the pH. Now the HA, just like the A- is a part of that 125 milliliter buffer solution. So we're going to use the same volume there of that, multiply that by its concentration. That was 0.35 moles per liter, or molarity there. And we get 43.75 for that one. I'll try to just do the right number of M's there for my millimoles in that case. All right, and so now we're ready to do the ice calculation on this. Initial, change, and equilibrium. For the HCl, that's the 3.75. For the A-, 22.5. And then for the HA, 43.75. All right, with a buffer system, you're going to have some amount of both the weak substance and its conjugate in there at the beginning of that reaction in the initial amounts. All right, now for this, we're going to do our change. The reactants always decrease. Assuming you've set the equation up correctly, your reactant should decrease and your product should increase. Don't forget that part. A lot of students have it decrease across the board and they get the wrong answer. The products are increasing as the reactants are decreasing. And just like we did in the strong acid, strong base example, the change is going to be the smaller of your two reactant amounts. This particular problem, that is the HCl. So we're going to decrease by 3.75 for the HCl, decrease by 3.75 for the A-, and then we increase by 3.75 for that HA substance. All right, so again, don't forget that part. So the HCl, that goes to 0. The A- decreases to 18.75 when you do the math there. And then you're going to add these together. That comes out to 47.5. And again, these are millimole amounts. The change should always be the smaller of your two reactants when you do this. All right, and if you'll notice, what are we back to? What kind of solution do we have left over? It's not just a weak acid solution. It's not just a conjugate base of a weak acid. It's a solution that contains both of those. It's another buffer system. It's the same buffer system we did before. All right, if I back up for a second, it's this same buffer system. And so if it's a buffer solution, you can use the Henderson-Hasselbalch. What's that pKa going to be? It's going to be that same 5.62 amount. All that's changed are the amounts that we're going to plug in here for the A- and the HA. All right, so let's come back over here. So it's still pH equals pKa plus the log of the A- over HA. Keep in mind, Henderson-Hasselbalch is not an equilibrium constant. All right, that ratio is not products over reactants. The ratio is the conjugate base over the weak acid for this pH version. All right, so keep that in mind. pKa, again, is the negative log of that. That we said earlier was 5.62, right? Again, that we got from right over here. We took the negative log of 2.4, 10 to the minus 6 is how we got that 5.62. So we'll plug in 5.62 there, plus the log. A minus is 18.75 now, and HA is 47.5. Notice I skipped one of my 5 steps. One of the 6 steps. It's step number 5 that I skipped, and that was to find the concentration of the remaining pH players. You can do that. You would just divide the 1875 and 47.5 by the total volume. But it's not necessary when you're dealing with a buffer solution, since, as we talked about earlier, a buffer ultimately depends on the mole or millimole ratio of A minus to HA, and that's what we've got here. The millimole, as long as they're both in millimoles, you're good to go. That unit will cancel out. And so when you do that, we come up with a pH of 5.22. All right, take 18.75 divided by 47.5, take the log of that, add that to 5.62. There's our pH. Does that answer make sense? Yeah, something you always want to ask yourself. Does your answer make sense? And I know that's hard when you're first starting out because you haven't done a lot of these. But think about the pH of our original buffer. That's why I wrote it up here. It was 5.33. All right, that was just this 125 milliliters of buffer. What did we add to the buffer? We added some strong acid. And what do acids do? They make the pH go down. And it did here. It went from 5.33 to down to 5.22 for this particular system. So the acid did a little bit of work on this. It decreased the pH just a little bit. But that's the key with buffers, is we don't want to see a huge change in the pH. All right, buffers, they're like pH shock absorbers. They keep the pH from going up or going down a lot. All right, if you add an acid, the pH is always going to go down. If you add a base, the pH is always going to go up. It's a matter of how much up or down it goes. And with a buffer, it minimizes that change in pH compared to what it would be for an unbuffered or just plain water. You'd see a huge change in the pH, couple of pH units. Here, it was barely a tenth of a pH unit. All right, let's try one more example and then we'll be done. All right, how about the pH when NaOH is added to the same buffer? So I'm using the same buffer once again here. And again, you'll see this. Let's just remind ourselves the original buffer we said was what? 5.33. Yep. All right, so 5.33. So what do we expect to have happen here if we add some strong base? That's what NaOH is. pH should go up, right? Let's see what happens. Let's start with the reaction. So again, start with what you're adding into that buffer system. It's the strong base. So here, which part of the buffer? We've got 2 choices or 2 things to choose from. We've got the weak acid component or the conjugate base component. We're adding a base in, that's sodium hydroxide. That's going to react with the acid part of your buffer, the thing with the hydrogen, not the thing missing the hydrogen. All right, the acid's got the extra hydrogen on there. So we're going to donate the hydrogen. H plus goes from the weak acid over to the hydroxide ion. It's a one-way reaction. We get some sodium ion. That's really just a spectator here. We get some A minus ion. That's what we have left when the H leaves the HA. And we're going to get some water. All right, so there's our reaction for this. And so what are the pH players? The strong base is a pH player. The weak acid is a pH player. And one more, the conjugate base. Don't forget that conjugate base. When you're dealing with a buffer, there's always 2 parts, an acid part and a base part. That's what makes it a buffer, and they're both weak. All right, so if you've got a weak substance on the reactant side, automatically realize you got a conjugate substance on the product side that's also going to affect the pH of that. All right, let's do our millimole amounts like we did before. So for the NaOH, it's going to be volume times concentration there. I used 19 milliliters, and it was 0.48 moles per liter there, and I got 9.12 millimoles of NaOH there. All right, for the HA, this is the same as it was before. For the HA, it was 125 milliliters times its concentration was 0.35 moles per liter, and that's 43.75. So we're back. I'm using the same original buffer solution that we had before. And then for the A- ion, same 125 milliliters that the HA is dissolved in. And we had a 0.18 mole per liter concentration there. That came out to 22.5 millimoles. All right, now we're ready to do our ice calculation. Initial, change, equilibrium. All right, for the NaOH, it's 9.12. For HA, 43.75. And for the A- over here, 22.5. Once again, assuming we've set everything up correctly, the reactants will decrease. What are the products going to do? That's got to increase for us. The change, once again, it's the smaller of your two reactant amounts. Even if your product amount is smaller, it's going to go up. All right, it's not a part of that change calculation that you're doing. So in this case, that's the NaOH, the 9.12, 9.12, and 9.12 there. So the NaOH goes to 0. I always like to say at this point, the buffer did its job. It got rid of that strong base. All right, and the HA then drops down. It does decrease a little bit to 34.63. And the A- increases to 31.62 when you do the math there. All right, and so what kind of solution do we have left? Starts with a B, ends with uffer. It's a buffer solution. All right, you've got weak acid, you've got its conjugate base in there. All right, it doesn't matter which side of the equation those are on. If you got both of them in the solution doesn't care which side you wrote them on your equation. If they're both there, it's a buffer solution. If it's a buffer solution, you can use the Henderson-Hasselbalch. Henderson-Hasselbalch does not depend on what substance you've added to the buffer. It depends on the buffer. And it's still the same buffer system that we had all the way back at the beginning. All right, all we've changed are the mole or millimole or concentration amounts of the HA and A- amounts. The pKa is still 5.62. All right, and so we're still going to use the same Henderson-Hasselbalch. pH equals pKa plus the log of A- over HA. All right, that's the same equation I wrote all the way back at the beginning here. It's the same equation that we use. Remember, it's not products over reactants. Here it happens to be, but again, it's the conjugate base over the weak acid. The pKa is still the same 5.62. That's just because of this weak acid HA and its Ka value. Plus the log of the A-, that's 31.62. That'll go in the numerator. Again, that's millimoles divided by the 34.63 millimoles. That goes in the denominator. And you do the math on that, and you come out to 5.58. All right. Again, does that answer make sense? Well, what did we add in? We added a strong base. Did the pH go up? Yeah. Here was the pH. 5.33 was the original pH of the buffer. And we added some strong base to this. The pH did go up just a little bit, right, to 5.58. So it all makes sense. All right, so you got to practice these problems. All right, in my class, you're definitely going to see something like that on your exam. So you got to know how to do those buffer calculations by themselves. That's super easy. It's when you add an acid or a base to the buffer, that's when things get a little bit trickier. All right, so that's all I've got for this video. I'll see you in the next one.